All right, let's move on to the 2-bit equality comparator circuit, right? We just took a look at the 1-bit equality comparator circuit. And now we'll see what happens when both of our inputs are 2 bits, right? So with a 1-bit equality comparator circuit, we could only compare 2 possible numbers, 0 and 1, right? A could be 0, or it could be 1. B could be 0, or it could be 1, right? So we want to then start making circuits that represent larger ranges of decimal numbers, have more binary inputs. So in a 2-bit equality comparator circuit, both of our inputs will be 2 bits wide, right? A will be 2 bits, B will be 2 bits. And so 2 bits is 2 squared. That gives us 4 unique representations, so we can convert that and say that this circuit would compare decimal values in the range of 0 to 3. Right. All right, let's take a look then at that truth table. So we're going to label then A, right? A1 is going to be the most significant bit of A. A0 will be the least significant bit of A. B1 will be the most significant bit of B. B0, the least significant bit of B, right? So remember, this circuit is still going to answer the question, does A equal B, right? And so since we have then 4 total bits in input, 2 to the 4th is 16, we have 16 entries in our truth table. We can have these 16 unique binary patterns, right? And so if we were to start going through the truth table and filling this out, right, we would take a look at this. And so we'd say, well, when A is 0, 0, that's a decimal 0. And when B is 0, 0, that's a decimal 0. And we'd say, is 0 equal to 0? Yes, it is. Our output's a 1. Here, when A is 0, 0, that represents the number 0. When B is 0, 1, that represents the decimal number 1. And we'd say, well, is 0 equal to 1? No, it's not. As we go down, so for these first 4 entries, the decimal equivalent of A is 0, right? But then the decimal equivalent of B here is 2. Is 0 equal to 2? No, our output's 0. Is 0 equal to 3? No, our output's 0. All right, so as we go in and fill in the truth table, we're going to see that there's only 4 cases where A equals B, right? A will equal B when A is 0 and B is 0. A will equal B when A is 1 and B is 1. So I'm talking decimal numbers, right? You can see the binary patterns here, right? A will equal B when A is equal to decimal 2, so binary 1, 0, and B is equal to 2, binary 1, 0. So we get an output of 1. Finally, when A is 3, decimal 3, which is a binary 1, 1, that will be equal to B when B is 3. So we have 4 instances out of this 16 where our circuit then outputs 1. So let's go ahead and solve for those 1s. Right. And so I've written out the canonical sum of products form. If we were to put this into a K-map, it would not reduce. Right. So that's why I've written out the canonical sum of products form. Here we have then, this represents min-term 0, right? And then the next one represents min-term 5. And then we've got min-term 10, and finally min-term 15 here for the 4 cases then where A is equal to B. All right. Now the question is, can we reduce this in any fashion? Right? We can't reduce it through a K-map. Right? Oh. So before I go into that, sorry, the next slide is how would we write this in Verilog if we were going to do a canonical sum of products implementation. This is a rather long equation, right? It doesn't look long here in its binary form, but what I want to show you then in the Verilog form is that if we write the module, right, we'll still have then our inputs A and B. But now, because A and B are 2 bits wide, we have to specify their size. So here we specify the size in brackets. You have to use the brackets. And the size, we say, is 1 down to 0. So instead of saying 1:0, we say the size is 1 down to 0. I didn't make that up. It's just what people say, right? That means 2 bits, right? We have bit 0 and bit 1. And so every signal we put to the right of this size will then both be 2 bits. So A will be a 2-bit signal, B will be a 2-bit signal. Our output then just needs to be 1 bit, right? If you go back to our truth table output is just 1 bit. Here I just named the output A, EQ, B. Could have named it EQ, right? Now we're doing something different in here that we've not talked about in class before. We're internally declaring some signals. What I've done is I've broken up this equation into each of the 4 min terms, right? If we had 4 different min terms, so what I said here was I said, here's min term 0, not A1 ANDed with not B1. That is ANDed with not A0 ANDed with not B0. That is min term 1. Here's min term 5. Not A1 ANDed with not B1. These don't have to be grouped together, right? You don't need these parentheses. The reason I'm grouping them together is we're going to go back and we're going to see that we're going to take a look at this pattern of these pairs of behavior, right? But min term 5, once again, not A1 and with not B1 and with A0 and with B0. Midterm 10, midterm 15. So I've just implemented each one of these as a separate midterm, and I've assigned them to signals that I just named P0, P1, P2, P3. These are just intermediate signals in my circuit, right? In order to use then these additional signals that I've introduced that weren't part of our equation, right? We declare them up here with the keyword wire. They do not go in the port list because they are not inputs and outputs of the circuit. They are just internal to the circuit, right? And so P0, P1, P2, and I think my naming convention was product 0, product 1, product 2, product 3, right? We know that all of those min terms are ORed together, so I just simply said, right, or all of these results together. All right, so P0 ORed with P1 or with P2 or with P3. Assign that to my output EQ, except I need to fix that because, right, I named this AEQB here. Sorry, let me pop that up. Sorry, this should have been called AEQB. It has to match that because this is my signal to the outside world. Right. So sometimes to break up an expression, we simply write it in this form, right? And that just gives you an example of how to declare other signals within a module, because as some of our modules get more complex, we'll have to start declaring signals within the module. Right, so the new thing here, sizing the signal, declaring new signals inside, breaking things up. Now remember, this is representing hardware, so there is no order. This is all concurrently happening, right? If there's a change on the input signal A1, right, that change will be reflected in the signal P0. When as soon as that change is reflected there, that change is reflected here in the hardware. See, these are called wires, so you can just kind of think of these as wires connecting this to each other, right? And so that would be our canonical sum of products implementation for a 2-bit equality comparator, right? It's getting long and a little bit longer, lengthier, right? All right. Let's go then take a look at that canonical sum of products. So here's our min terms, right? 0, 5, 10, and 15. And I want you to take a look at the fact that we have some terms in common. This has A1 not, B1 not in it. This has A1 not, B1 not in it. So we're going to use the distributive law and factor that out. These two terms have A1, B1, A1, B1 in common. So we're going to factor those out. So once we do that, we end up with this expression, right? A1 not ANDed with B1 not, ANDed with then this internally, and A1, B1 that we factored out of here is ANDed with this expression, right? Let's take a look at this internal expression here. Now it's the same here, right? We could do a further factoring step. So if you look at this, this matches the pattern of an XNOR gate, right? It just is then the 0 bits being XNORed together. And remember, we said XNOR is the equality gate. And if you look at it, this is basically a 1-bit equality comparator, right? Both of these bits are A0 and B0. We're going to use the XNOR gate, which we said was an equality circuit. That was the circuit for our 1-bit equality comparator. So we'll simply replace then this expression with A naught or with B0 naught, right? Factor that out of here so that we end up with A1 naught ANDed with B1 naught ORed with A1, B1 because we factored this out, right? And we replaced it with this, and with this XNOR relationship. But now, if you take a look at this, this is another XNOR gate, right? This is simply A1 XNORed with B1. So we'll replace that as well. I just happen to use the commutative principle and put the A0s here and the A1s here. But our circuit now reduces to A0 XNORed with B0 ANDed with the result of A1 XNORed with B1. And what we're saying in effect, right, is when A0 and B0 are equal and A1 and B1 are equal, that A equals B. Right? That's what this slide is telling you. All right, we look at this equation, and if we want to state this in English, we say that A equals B when A1 equals B1, and, there's our AND gate right there, and A0 equals B0, right? A1 equals B1, XNOR gate. A0 equals B0, XNOR gate. Right. And so this is just an English word description of what we've observed, the behavior we've observed. And so we could more simply implement the circuit rather than that really long sum of products expression with 2 XNOR gates and an AND gate. Right. And let's go ahead and actually do that in Verilog and verify that it works. Right. And I do want to go back, let's go back to the truth table here. And let's look at these pairs. Look at this. We said when A1 equals B1 and A0 equals B0, our output is a 1. Here when our output's a 0, well, A1 equals B1, but does A0 equal B0? No. If you go through every case where A1 equals B1, and A0 equals B0, you'll see that our output's a 1. Right. All right, so let's go ahead and go into Quartus and let's try to create this 2-bit equality comparator with this relationship here. All right, so let me bring Quartus back. All right, and so this is the old project that I was using before in part 1 for our simulation. Let's create a new Verilog file, so new. File new, Verilog HDL. All right, I'm going to put some comments in here. And this is a 2-bit equality comparator. Right, and we say, does A equal B? Right. And let's define then our input. Our circuit input is, you don't have to use those asterisks, I just do out of habit. Well, A is 2 bits, right? B is 2 bits. And we'll call AEQ, so output, AEQ B is 1 bit. And so our module, keyword module, and I'm going to call this EQ underscore 2-bit, input wire 1 down to 0, A comma B, output wire AEQ B, semicolon, every module ends with end module. And let's define our implementation. So continuous assignment statement, assign AEQB is the name of our output signal, assign to that. Okay, so we said that we want to XOR A0 and B0. So A0, so now when we refer to the individual bits, I can't just say AX or B here, right? Or sorry, AX nor B. Right, there's our XNOR relationship because A and B are 2 bits wide. What I need to say is our equation A0 XNOR B0. Right? And so when we when we size an expression, the size always goes on the left-hand side. When we refer to the individual bits within a multiple bit expression, we still use these square brackets, and then we use the bit number to say which bit we're referring to. And then we have our AND relationship, and now we want to then A1 xnor with B1. All right. That should be it for our equation. Let's go ahead and save our module. So in Quartus, whenever you create a Verilog module, you want to save the file with the same name as your module. So I'm just going to copy that. I'm going to say File, Save. I want this in my project. It goes to my project folder I've been working in, the Q2-bit. All right. And so here in the Project Navigator window, let's go ahead and take a look at our files. All right, so we've got some block diagram files and other files in here that not really currently using, some other Verilog stuff we're not using. I think we can ignore that for now. Here's our new one. I want to make this the top level. We're going to run a simulation, compile against it. So I'm going to select it, right click, say set as top level entity. Once I do that, then right, I can go ahead and I can run analysis and synthesis. If you want to verify it's your top level, instead of the file view, you can always go to the hierarchy view, and notice then that shows up as our top level. There's nothing dependent on it. All right, let's run analysis and synthesis. We'll ignore the warning about the parallel processors. It's okay to ignore. All right, and let's see if we can run a simulation. So I'm going to say File, New. All right, we had our other vector waveform, but let's write a new one. So, okay. All right, simulation, so edit, set end time. We have 16 unique input. So we have 4 bits. I want to go with clock periods of 10, 20, 40, 80. So I'm going to say, let's make this 80 nanoseconds. Say OK. Right click here, insert node or bus, node finder, list all. So these are all the signals. Then in our top level, select them all, say OK, OK. And notice now when we have multiple bit signals, you can either, this refers to this by A, but you've got A1 and A0. This refers to this by B, B1 and B0. Our output's here in the middle. I'm going to drag the output down here. I want A and B to kind of show up like this. And now we're going to generate our signals. Now in our truth table, this was the least significant bit. So I'm going to take this and give it the shortest clock period. So overwrite clock, 10 nanoseconds. OK. Generating the zeros and ones. Select this one. Let's double the period. 220. Right. Now here in A, let's select A0. Let's double that 20 to 40. And here in A1, let's double that 40 to 80 nanoseconds. All right. Now this is showing us individual values of A and B. You can see that A holds to 0 while B goes from 0 to 1 to 2 to 3. All right, which is what we're doing with our truth table. All right, let's go ahead. So all this did was generate the 16 possible inputs from the truth table. Let's save this. File save. Wants to name it waveform 1. I'll say OK and hope it works for me. Simulation, run functional simulation. Okay, it worked. All right, so let's take a look at our circuit now. Right, we said there's 4 times when A is equal to B. So here B is 0. So in all 4 of these cases, from here right to here, A is 0. So when A is 0 and B is 0, our output's 1. When A is 0 and B is 1, our output's 0. So every case where A is not equal to B, our output's 0. Right here, where our input is 0, A is 1, B is 1, our output's 1. Zeros everywhere else. A is 2, B is 2, output's 1. Everywhere else we have zeros. Finally, the fourth case, when A is 3, B is 3, then our output is 1. So you can see then that our Verilog circuit was correct. All right, so that is one way to then go ahead and create that, right? We ended up with these simple, well, this equation here that we derived through Boolean algebra. But we want to take a look at another way to use this circuit, a structural representation. All right, so let's go back over to our slides. Like we said, we've observed that we're comparing pairs of bits, right? We're comparing A0 and B0 to see if they're equal. We're comparing A1 and B1 to see if they're equal. When they're both equal, then our output is a 1. So we derive then this English expression. Well, we can build a structural implementation of this 2-bit circuit using 1-bit equality comparators. If you take a look at this, this is simply a 1-bit equality comparator for this pair of bits. This is a 1-bit equality comparator for this pair of bits. And the results, the outputs of each of these are ANDed together. So if we were going to use our block symbols, the circuit would look something like this. So this block symbol represents a 1-bit equality comparator. This block symbol represents the same 1-bit equality comparator. And so if you take a look at this, now my inputs then, A and B, the pins we label as 2 bits wide, 1 down to 0. These thicker wires mean it's a bus, meaning there's more than one wire in it, right? And so that this wire represents that it's carrying both signals, A1 and A0. Well then, in Quartus, then if we just go ahead and label then this single wire that we tap off the bus here, so we label this and tell it to go ahead and pull off the wire A1. Same way here, this bus that represents B, the 2 bits of B, we label this wire B1, and both of these are inputs to an equality comparator. What comes out of here then is the result of does A1 equal B1. In this particular case, I labeled the wire EQ1. Here, we're comparing bits A0 to B0, right? The output of this circuit is does A0 equal B0? We said then we need to AND those two values together after we compare bit pairs. We AND that together, and our overall output then here I named EQ, right? This will actually give us then the same representation as that Verilog module we wrote. And we can write a Verilog module instead of using these block symbols, using 1-bit equality comparators. Now, this looks like a bit more trouble for a 1-bit equality comparator. But what we want to start thinking about is if we were to go to a 3-bit equality comparator, right, then, well, we don't want to probably draw things schematically. We're going to have to add more symbols. We don't want to necessarily write out a truth table because, well, if A is 3 bits and B is 3 bits, we have a total of 6 input bits. 2 to the 6 is 64. We have a 64 input truth table. This is getting really big to start deriving Boolean equations, right? All right, and sorry, that slide shows you that you can make a symbol for the 2-bit equality comparator. You could take this circuit you drew, create a block symbol for it, and use that as a 2-bit equality comparator. But what we want to do is we want to learn how to do this with Verilog, right? So we'll do that in the next tutorial then, how to create that 2-bit equality comparator with Verilog. For now, just think about this relationship.